Hiya, it's Mr. Baker here, and today we're going to be looking at gas pressure and temperature. Okay, so today we're going to be looking at this question. We're going to be looking at how does a gas exert pressure and how is this linked to temperature. Okay, so how does a gas exert pressure? How does it create this pressure? So a gas consists of molecules in constant random motion. When a molecule collides with a surface, it reverses its direction due to the force exerted on it by the surface. So here we've got lots of particles in a gas, maybe air, and you can see that they're going in different directions. When a particle is going towards the surface, let's say it's the wall, we've got a particle of air going into the surface. What it's going to do is going to basically bounce off, isn't it? So these particles, every time they smack into the wall, they're going to exert a force on the surface. So it exerts a force on the surface. The surface, because of Newton's third law, exerts the same force, an equal and opposite force, onto that particle. And the pressure exerted by the gas is equal to the total force exerted by the molecules on a particular area of the surface divided by the area. So in other words, depending on how many particles there are smacking into that surface and how big that surface is, depends on what the pressure is going to be, because pressure equals the force divided by the area. So each of these individual particles is going to hit into the surface, rebound off, and they're going to exert a force onto the surface. The surface is going to make them rebound off. Depending on how many times they hit into the wall, how quickly they hit into the wall, and the surface area of the wall, all of those things will change the pressure. So if you've got a small surface area and you've got lots of particles hitting into it, you're going to have a large pressure. If they're not hitting into the wall very often or not very fast, then they're going to have less force, so there's going to be less pressure. Now we've just said that particles are moving around in a gas at random and they're smacking into the surfaces, and we've kind of just said that, that's fact. But a couple of hundred years ago this wasn't a known fact, and it wasn't until somebody called Robert Brown actually sort of discovered what was happening to the particles in a fluid that people even thought about this. And actually it didn't happen straight away that was the explanation of what was happening. People didn't really understand what was going on in Brown's investigation, which I'm going to describe now to you. So until actually the kinetic theory, which we've looked at in previous lessons, came along, even his little investigation wasn't really explained. So Brownian motion describes how particles in fluids move randomly, and this is a little demonstration of what you can do, how you can set up an experiment to actually see this happening. So if you have a little box, call it a little cell, glass cell that's filled with smoke. If you illuminate it, if you let some light go through it, and then if you look through, so if this is a glass top and you look through with a microscope, then you hopefully would be able to see this kind of thing happening. You'd basically see the individual smoke particles, and they would do this. They'd sort of move completely at random, bouncing off stuff that are invisible to anybody, to you, even looking at it with a microscope. And this was really what Robert Brown saw. He saw a similar kind of thing, the random motion of tiny particles in a fluid, and he called it Brownian motion after himself. He used a microscope to see it in the random motion of pollen grains floating on water. And he couldn't explain what was happening. And in fact, like I said, until the kinetic theory came along, it couldn't be explained. I'll say he sort of named it after himself. I don't think he actually named it after himself, but it was named after him. So it was named after him because of the investigation that he did with these pollen cells. So this is an animation of the kind of thing that you might see. We've got these three particles here, and you can see they're moving around. They're not moving very quickly, they're moving fairly slowly, but they kind of like are bumping into something. They're moving around randomly, and it's difficult to see why that is. But this is the kind of thing you would see if you were to look through one of those smoke cells. You would see this kind of thing, and you would see these particles moving around at random. So I've increased the energy, the speed that they're going, just so that it speeds up a bit. You can see they're sort of randomly moving around, sometimes in the shot, sometimes out of the shot. And if I trace the path of what's actually happening, you can see they trace out this sort of random path. And what they're actually doing, so this would be like a large smoke cell, and it'd be bumping into all the particles of air. And this random nature of these particles moving around led to our explanation of gas pressure. And this is why it's so important. And you can see that as I've increased the energy, they're going faster. So as they're going faster, they're going to be smacking into these other particles. They're going to be potentially smacking into the sides more often. And as we've said, gas pressure is caused by these particles, their individual forces hitting into the surface over a certain area, and that's what causes the pressure. So it's really this discovery of Brownian motion that led on to, and with the explanation of kinetic theory led on to the explanation of gas pressure. So I want you to have a look at this little animation now. So in here, so we've got like a glass container filled with looks like helium particles, and you can see that they are moving around at random, hitting into the surface, sometimes hitting into each other, and causing pressure. Wherever they hit into the surface, it'll be causing gas pressure on that surface because of the force of them hitting into it and rebounding off. This whole lesson, what we're looking at is how does temperature affect the gas pressure. So I'd like you to have a little think, have a little prediction. What do you think will happen? So I've got a graph which I'm going to show temperature on the x-axis and pressure on the y-axis. So I can change the temperature. It's going to start off warmer, and then it's going to get cooler. So I want you to think about what's going to happen as I reduce the temperature. What do you think is going to happen to the pressure? So just have a little guess what's going to happen to the pressure, and then see if you got it right. Okay, so I'm going to reduce it. Okay, so you can see that as the temperature decreases, the pressure decreases, or vice versa. If we were to do it the opposite way around, as the temperature increases, the pressure increases. And it's a straight line as well, isn't it? So they're proportional to each other. And you can see what happens to the speed of the particles. So at the moment, the particles are moving around fairly slowly, hitting into the surfaces. So as they're moving around slower, they're obviously going to hit into the sides less often. If they're moving around slower as well, they're going to move and hit into the side with less force. So there's two things here. We've got less times they're actually going to hit into the surface, and there's going to be less force every time they do it. So yeah, the pressure is going to be less, but it depends on the temperature, and we know that the temperature is really just a measure of how quickly the average particle is sort of moving around. So as those particles are moving around slower, then the temperature is going to be less. If they're moving around slower, then the pressure is going to be less because they haven't got as much force and they're not going to be hitting into the sides as much. So if you can see, like, if I increase the temperature, you can see what happens to the particles. They're moving around quicker, hitting into the sides more often, and with more force, so the pressure is going to be greater. And if I move that even higher, so the temperature is even higher now, the particles are moving around even faster, causing even greater pressure. Okay, so the temperature is proportional to the pressure. So as the temperature increases, the pressure increases. So just to finish then, so we've said that temperature and pressure are proportional to each other. So if you look at these two graphs, I want you to look at what's different. There's a couple of things that are different. So can you see, so we've got pressure on the y-axis for both of them. They're measuring temperature on the x-axis as well, but actually it's a slightly different scale. So on the scale on the left, we're looking at temperature measuring in something called Kelvin, capital K. And on the graph on the right, I don't know if you can see it, but it's the temperature in degrees C, so Celsius or centigrade. So if you looked at both of these graphs, we could definitely say yes, as the temperature increases, the pressure increases, and it's proportional. If we use the graph on the left, though, under what circumstances is temperature directly proportional to pressure? So when can we say that yes, for sure, the temperature and pressure are directly proportional? Well, it's when we have this graph on the left. So when the pressure and the temperature are proportional, but actually that graph also goes through the origin. It goes through 0, 0. So as the temperature increases, the pressure increases, and it goes through 0. We know that the temperature and the pressure are directly proportional. And just finally then as well, what's the temperature when the pressure reaches 0? Well, it's 0, isn't it? So it's 0 and 0 on the one on our left. So 0 Kelvin means basically if temperature is a measure of how quickly particles are moving around on average. So if there's no pressure, that means that the particles can't be moving around. So if they're not moving around, then the temperature must be 0. So 0 Kelvin is actually sort of a theoretical temperature. We can't reach it. But it's at minus 273 degrees Celsius, you would get to 0 Kelvin. And that's where the pressure would also be 0. So you can actually look at this and you can work backwards from these graphs and find out what the temperature would be when the pressure is 0. And this is how we found that the temperature would be minus 273 degrees, which is, on this scale of Kelvin, 0. Okay, so that's it for this one. So we've looked at gas pressure and temperature, and hopefully you can do the following kinds of things. You can describe a model of a gas and how it causes pressure. You can describe how Brownian motion gives evidence for our model of gas pressure. And you can also explain how temperature and pressure are related. Right, well that's that for this one. Thanks very much for watching it. I've been Mr. Baker, and I will see you next time.